Good afternoon, everybody. Am I getting recorded? Okay, great. It's my great pleasure to welcome my friend, Professor Onur Mutlu from ETH Zurich. I've known Onur for quite a long time. I think I met you first when you were a student, or maybe you just graduated and you were visiting Stanford when you were at Microsoft Research, right?
Yes.
Yeah. So then, since then, we have been in close touch, and as you know, that Onur is. To say that Onur is a rock star is an understatement. He's a rock star in computer architecture, and he has received numerous awards. If I had to read those awards, then we'll be out of time, and the seminar will end. But I feel really, really happy that he received an important honor in my advisor's name. So and Onur will be spending a year at Stanford on sabbatical. So this is a unique opportunity for the Stanford folks to interact with him and learn from him. So Onur, thank you very much and welcome.
Thank you, Subhashish.
Yeah.
Thanks a lot. Thanks for inviting me and hosting me as well. Yeah. Okay, let's get started. So I'm going to talk about RowHammer, RowPress, and beyond. And I have this title over here that probably everybody knows the answer to, but maybe we can discuss that at the end. How many people know of this bridge? Okay, what is it? The common arrows. How many people have been over it? Probably zero, because this is what happened to that bridge in 1940. It's a Bitflip, and this is a Bitflip that's clearly in important infrastructure like bridges, and it's taught in civil engineering classes as a classic example of how not to build bridges, let's say. But we're going to get back to bridges at the end of this talk in a little bit. But this is also an example of a reliability issue that caused a safety and security problem. And in this talk, I'm going to cover a reliability issue that caused a safety and security problem as well. I'll also ask you this question. How secure do you think these people are? They look quite happy. You don't need to answer. If they get a Bitflip, they will not be happy soon. So I think of security as preventing unforeseen consequences. You can replace that security with safety over here as well, probably. Now, this is robustness. Yes, exactly. I had that in my abstract. I'm going to get back to robustness. Essentially, robustness is safety, security, reliability combined together. This is Mr. Bean. You may have seen this, and clearly he is foreshadowing the future. And if you have infrastructure that looks like this, which is going to be much more common than bridges, of course, driven by somebody else other than Mr. Bean pulling strings. And if you get Bitflips in this, we may not be very happy going into the future. And this infrastructure will be all over the place. There are billions of devices that are going to be around us. Okay, so what is RowHammer? Why am I showing you all these pictures? Essentially, RowHammer is the fact that you can predictably induce Bitflips in commodity DRAM chips. The first time we tested this problem, we saw that more than 80% of the tested chips were vulnerable. Today, it's 100%, but I'm going to give you the story of it also. And interestingly, this is, as far as we know, the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. If you know of something else, please let me know. I'll correct my slide. And people are writing interesting articles like this. Forget software, now hackers are exploiting physics. I like this because this kind of gets to the core of the problem, if you will. So I'm going to give you a little bit of story of how we stumbled on this and what we've done and what people have done. And hopefully we can have a good discussion. Feel free to interrupt me with any question that you may have at any point. So we've been working on memory reliability problems for a while. I was invited to give this talk at the International Memory Workshop in 2013, where we argued that these problems are going to get much worse, and we really need to take a systems and architectural perspective to solve these problems. So what is the problem that we're going to look at specifically in the memory side? There are a lot of issues in other memory technologies as well, but we're going to focus on DRAM. And if you look at DRAM, DRAM stores charge in capacitor. Let me see. Yeah, this is not working very well, so I'm going to use my pointer over here. You need to have a storage device and you need to have an access device, and both of these need to work very well, essentially reliably. And as you reduce the size of the circuit, the reliability, maintaining that reliability becomes a challenge, and you get noise, a lot of noise. And as a result, capacity, cost, and energy were hard to scale in DRAM. And this is a virtual picture, if you will. The physical DRAM looks like this. It's like a honeycomb structure, which is very interesting also. So there are a lot of interesting effects that we're not going to go into. I'm not going to go into the device level over here, but I'd be happy to talk about that. Basically, DRAM is used in all memories today that we build, all main memories. And we wanted to understand the reliability issues. This is one of the large-scale studies that we did with Facebook in 2015, that was published in 2015. What we did was we analyzed all of the memory errors in all of their data centers. This is actually a lot of memory, a lot of servers. They didn't allow us to publish how much memory, how many servers, because they were worried that this would give out the size of their fleet and affect their stock price, etc. But imagine that this is a nice correlational study. So what we found out is that the DRAM chip density that's employed in the server is strongly correlated with the server failure rate that you're getting at the system level, at the application level. We can go into a lot of detail over here. I'm not going to do that. But basically, the denser the DRAM chip, you get more errors. And this errors happens because the cells are smaller and cells are closer to each other. So there are a lot more reliability and noise issues. And you can read the paper if you're interested. People have written papers that build on this paper also from AMD, Microsoft, etc. that are interesting. So of course, with a large-scale study, you cannot really pinpoint some of the issues. So we also wanted to build an FPGA-based infrastructure to understand some of the low-level issues that we can that happen with DRAM. And we're going to look at retention failures and latency and RowHammer in this. So basically, these are FPGA-based infrastructure where you can modify the memory controller, and the memory controller can change the commands that you can issue to DRAM so that we can test essentially anything that the interface allows. By violating the timing parameters, for example, by not refreshing DRAM, we can figure out different things. And this is the infrastructure that we use to do a lot of the RowHammer studies. We open sourced it in 2017. And more recently, we actually open sourced a newer version of it in 2022 that can test DDR4 chips. If people are interested in actually doing studies on DRAM, we'd be happy to support it. We've been supporting people to do that. So why did we build this infrastructure? We actually wanted to test these reliability issues. And one of the major reliability issues that we wanted to test was data retention. If DRAM is dynamic random access memory, it needs to refresh frequently. And we said, basically, if you refresh frequently, if you actually reduce the size of the cell and the cells get closer to each other, you need to refresh things much more frequently. And we wanted to avoid that. And we wanted to understand how the retention time profile of DRAM looks like and exploit that. And this is actually very well known, but we validated it. Most of the DRAM cells don't need to be refreshed frequently. And we wanted to understand, can we actually enable real mechanisms that avoid refreshes in DRAM so that your power doesn't explode and your battery doesn't die, for example, because of DRAM refreshes. My cell phone, for example, is refreshing its DRAM in my pocket right now, unnecessarily, I would say. Okay, I'm not going to tell you the story about refreshes. There's actually a very, very interesting story in retention over here, because this is a very much tougher problem than this picture shows. It's very difficult to identify these cells that can be refreshed at different rates. But we've written papers about it that I'm going to skip. So while we were doing these studies, we were actually doing a lot of studies with flash memory as well. I'm going to show you a picture of infrastructure with flash memory. And in flash memory, there are a lot of errors. And one of the issues was read disturbance errors. And together with Intel, we wanted to actually analyze the read disturbance errors in DRAM as well. So what is RowHammer? Essentially, RowHammer is a read disturbance mechanism. This is an array in DRAM. You have rows of cells. Each cell stores 1 bit of value. If you want to read a value in one row, you need to open or activate that row, meaning apply high voltage to that word line. Now, if you want to read some other row, you need to close this row. It's called pre-charge in DRAM, apply low voltage to that word line. Now, if you keep doing this repeatedly, open, close, activate, pre-charge, activate, pre-charge, activate, pre-charge, essentially we found out that physically adjacent rows get bit flips in vulnerable cells. And clearly this should not be happening, right? Because nothing should be changing in memory. We're just activating a row. But now you're actually corrupting data in nearby cells. This data can be belonging to your own application or some other application, the operating system. As a result, this is a data corruption problem that could affect your safety, clearly reliability also, but security also, because these bit flips can be taken advantage of, as I will describe in a little bit. So we call this the hammered row. We call these the victim rows. And we show that essentially more than 80% of the chips that are manufactured by 3 major manufacturers are vulnerable to this problem. There are only 3 major DRAM manufacturers in the world. There are some others that are interesting, but they're also vulnerable, by the way. It's interesting. Okay. Yes.
Can you go back?
Yeah. Sorry.
What do you mean by 10 million errors? Is it over a certain time?
It's
like number of bits?
Over a certain number of bits. I believe a bank in this case. Yeah, don't take these numbers so literally. It's based on some experiments, but certain hammering pattern and certain number of bits. Yes. I don't know the exact like bank size, etc.
Spatial.
Exactly, it's spatial, certainly. Yeah. Yes. So here, for example, it's errors per 10 to the 9 cells over here. It's kind of that metric. Yeah, so this is also a scaling ground because the chips that we tested that were manufactured before 2010 were not, at least we were not able to induce Bitflips, RowHammer redisturbance Bitflips like this. But the chips that were manufactured in 2010, where we showed the first appearance of these Bitflips, and all the chips that were manufactured between 2012 and 2013 were vulnerable. I should also say that this is not the best way of inducing Bitflips. I'm going to talk a little bit more about a better way of inducing Bitflips. So there might be Bitflips in later generations that we weren't able to discover over here, for example. So you may actually find that anomaly. So why is this happening? In this talk, I'm not going to go into the silicon level device failure mechanisms, but crosstalk is one reason why this is happening. Electron migration and injection is another reason why this is happening. These are being studied also. But basically, the issue is DRAM cells are too close to each other. They're not electrically isolated from each other. Access to one cell affects the values in nearby cells due to this electrical interference between the cells as well as the wires used for accessing the cells. It's essentially cell-to-cell coupling interference. I like this high-level abstract picture. I use this actually for freshmen when I teach this to freshmen. For example, when you apply high voltage to a row, an adjacent row gets slightly activated as well. Clearly, I'm violating some low-level abstraction here. But vulnerable cells in that slightly activated row lose a little bit of charge. And if RowHammer happens enough times, charge in such cells get drained. And as a result, you get data corruption. Okay, and this actually has enormous implications on the software hierarchy because these Bitflips actually get directly exposed to the programming language, operating system, and essentially memory. It's very different from flash where storage, the Bitflips inside the storage don't get directly exposed to anything that's running immediately. Okay. So what's worse about this is that when we wrote the paper, we also released this code that showed that with this 6 lines of code, x86 code, you can actually induce these Bitflips. What this code does is it selects addresses X and Y such that they map to the same bank. And it basically avoids cache hits from the CPU and avoids row buffer hits in the DRAM. And ping pongs activates to X and Y, rows X and Y. And if the chip is vulnerable, you'll get Bitflips. In this paper, we also showed that if X and Y are selected such that there's only one row sandwiched between X and Y, you get a lot more Bitflips. This is called double-sided hammering. But in most of the experiments in our paper was single-sided hammering. Double-sided hammering is actually much worse because you increase the electrical interference that happens, coupling essentially. And we observed errors in real systems with that code. I'm not going to harp upon these real systems. All of the real systems that employ a good enough memory controller and this sort of memory gets Bitflips. So it's a real reliability, security, and safety issue. So in the paper, we said that basically the first sentence, as you can see, is memory isolation is a key property of a reliable and secure computing system, and access to one memory address should not have unintended side effects on data stored in other addresses. I strongly believe that. And we basically said that if this does not get controlled, someone can hijack your computer. And the good folks from Google Project Zero read our paper. They basically said, okay, we can do this. And they actually created a beautiful attack. I'm not going to go over this in detail. And this is actually copy-paste directly from their blog post. They have a beautiful Black Hat presentation about this also. They basically said they replicated the problem on a selection of laptops. And they wrote 2 programs. One is more interesting than the other. One was able to induce Bitflips and essentially escape the sandbox of the Google native client, virtual machine essentially. But the other one was as a user-level process, it was able to gain kernel privileges in x86 Linux. So the way they achieved this was they were able to hammer page table entries that point to the page table of the program, and they induced Bitflips on the page table entries that point to the page table of the program. And by flipping the right bits, they would gain write access to the page table, which is essentially the protection mechanism that we have in virtual memory today. And once you gain write access to your own page table, essentially all bets are off. You can do anything to that computer. And it's a beautiful paper. I recommend people to look at that Google Project Zero work. Later, this became famous as the RowHammer vulnerability. I like this written by a famous hacker on Twitter. It's like RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations open the door you were after. So if you're kind of magically stuck in this room, don't worry. Stop banging on the walls and hopefully magically the door will open if RowHammer is in effect. Was there a question? Yes.
If I go to my neighbor and start hammering,
yeah.
Say what's wrong with you. So isn't there an easy fix for this? I mean, there's no application that requires this, so can't you just catch somebody?
Yeah. So we're going to talk about solutions. Yes, we're going to get to the fixes. It looks easy, but there's a story behind this also. Very good. Any other questions? Okay. Yes.
Were they able to target specific bits, like using certain patterns, or was it just random until they got it?
Well, they crafted a special attack because this is not easy to do. So they sprayed the memory with page tables so that they increase the probability of the attack. So in the end, it's a probabilistic attack, yes. But if you attack, for example, just the right enable bit in your page table entry that points to your own page table, that's 1 out of 64 bits. The probability is very low. But if you spray the memory with many page tables, now you change the pointer to a page table entry, and you actually increase the probability of the attack significantly. Yeah, and then later, a lot of clever works in security ensued. So these folks from TU Graz, for example, showed that they could gain unrestricted access to systems of website visitors by doing this on JavaScript, which is interesting. This is actually a nice work from Kaveh Arzavi's group, who's at ETH right now. Basically, they showed that they basically created an app, and this app was able to hammer your memory and take control of your phone, because by exploiting some deterministic memory allocation patterns. I'm not going to go through these all in detail. People accelerate this using GPUs. People were able to do this using the remote direct memory access interface across the network. And this is another paper that talks about that. Even if you cannot take over another system, this paper showed that you could break confidentiality. By using RowHammer Bitflips, they could read someone else's memory, private memory that they should not be able to read. And more recently, people have been also looking at Bitflip attacks using RowHammer on neural networks. And otherwise nice neural network inference engine, accelerator, or CPU that's reasonably accurate may become actually completely inaccurate if you actually induce these RowHammer Bitflips. And there are a lot of works in this area. These are some examples. And I could go on and on in security community, but maybe this is another attack to your computer. Or maybe this is another solution. Of course, that's a joke. Okay, so we've been writing a lot of papers on this. I'm first going to talk about some initial understanding that we've developed, and then we're going to talk about what happened afterwards. But feel free to ask questions. We can make this more interactive. So this was the first RowHammer analysis, and this is the infrastructure that we used to actually analyze RowHammer. We tested 129 modules that were manufactured in those years, as you can see. And I'm not going to go through all of the results. I'm going to pick and choose some of them. This is an interesting one because we're going to look at the logical adjacency of the aggressor and victim rows, not the physical adjacency. Logical adjacency means, from the memory controller's perspective, where are the addresses? Is the aggressor adjacent to the victim? In most cases, they're one apart, meaning they're adjacent. But there are some cases where they're not adjacent. Now, this means we hypothesize that this is because there's some internal remapping of row addresses that's going on in DRAM for fault tolerance reasons, for other reasons, etc. That logically you're not adjacent. Now, what's the significance of this? The significance is that if you actually want to implement a defense in the memory controller, you don't know where the rows are. You need to figure this out first. So you need to reverse engineer, or you need to come up with an interface where the memory exposes the adjacency of the rows, which DRAM manufacturers are, in general, very against doing, let's say. And we can talk about that also. Okay, so another characteristic. This is actually real chips. These are all data from real chips from our 2014 paper. So, okay, you can say, okay, I can reduce the frequency of activations to the DRAM, and I can get rid of this problem. And you're absolutely right. And we wanted to test this. Basically, the way you activate DRAM at the time was every 52.5 nanoseconds, you can issue and activate. If you reduce that to every 500 nanoseconds, in the chips we tested, you could actually get rid of this problem. So this is called throttling of the applications. This is a bad idea if you apply it across the board, because this would reduce your performance greatly, as you can see. And basically, here, these are the worst chips that we tested, and these are the worst errors. Basically, you can actually get rid of all of the errors that we've seen. But remember that our patterns may not be the worst at the time. So this is actually much worse. So this is not a great solution, but we're going to get back to this. You can say, oh, I can actually increase the refresh rate of DRAM. And this way, if I increase the refresh rate to a level, hopefully someone will not be able to activate a row enough times before the cells get refreshed, right? And if you do that, yes, you actually get rid of the errors, as you can see, but you need to increase your refresh interval, refresh rate by 7x. And nobody wants that, because remember, the reason why we actually wanted to build our infrastructure was to get rid of refreshes. We don't want to add more refreshes to actually solve this problem. So, but we're going to get back to this refreshes, because this is the only lever that the industry had at the time to fix this problem. Okay, data pattern is interesting because different data patterns, because of the different charge levels they have across the cells, cause different coupling capacitance across the cells. As a result, different data patterns have different implications. You can see that you get 10x errors with the data pattern on the right. Okay, there are other observations here. I think errors are repeatable is interesting because if an error is repeatable, that means that you can figure out which bits are vulnerable, and this you can create a security attack based on which bits are vulnerable. ECC is not a good solution to this problem. We can get back to this. And as I said, double-sided hammering is much worse than single-sided hammering. Okay, so I'm going to tell you a little bit more story. Basically, this was 2014, and as the gentleman over there mentioned, that we thought this problem would be fixed, but it didn't get fixed, and we're going to talk about why. So we actually analyzed this again in 2020, and we show that it's getting much worse. I'm going to talk about that. It has many dimensions, and there are a lot of interesting studies that you can do. It affects the HBM chips as well, and perhaps more so, I'm not going to discuss that in detail. But let me jump into the solutions at the time, and then we're going to talk about some of these things. Any questions? Okay, so let's talk about solutions. So clearly, if you have such a problem, you need to have an immediate fix of the problem because there are all of these DRAMs out there, and you need to fix them, right? So clearly, we have limited possibilities because our memory controllers are not intelligent, let's say. But longer term, you can actually do a lot of things. You can change the DRAM, you can change the memory controller, you can change the software, you can change everything. We're going to talk about that a little bit. So in our ISCA paper, we propose both types of solutions, which are currently implemented in many things in different variants. We propose one solution as the best, but it's not working today. I'm going to discuss that also. So these are some solution approaches. I'm going to say that robust DRAM chips, this is in research, but it's very difficult to do this at low cost. Error correcting codes are a bad idea because error correcting codes are good for random errors whose causes you don't know. Here you know the cause exactly, so you can actually build a circuitry to fix the problem and save your expensive error correcting codes for things that you don't know. Increasing the refresh rate, and also error correcting codes are difficult to do because you get actually a lot of errors within a code word. Increasing the refresh rate is a bad solution today, but we're going to talk about that. Physical isolation is interesting, but a lot of the solutions actually are not secure. So the two major solutions that we are left with today mostly are reactive refresh, meaning you count how many activations you get for a particular row and refresh the adjacent rows in some way, either probabilistically or deterministically, or proactively throttle, meaning figure out which rows are likely to be hammered and proactively throttle accesses so that you don't hammer them more, such that you don't get a bit flip. Hopefully that makes sense. So there's a huge space in terms of cost, power, performance, complexity. You can have security over there also and safety in terms of the trade-off space. And people have been developing a lot of interesting solutions in the space. I'm going to show you some examples. So what did industry do initially? Essentially, they increased the refresh rates because this is what they can do. There's no other option, if you will. They cannot change the DRAM chips out in the field. Apple is nice because they actually credit our paper over here. And they don't say how much they increase the refresh rates, probably by 2x. So you can see that they closed the vulnerability, but probably they didn't completely fix the vulnerability. And it's Apple, everybody essentially released similar patches. So what was our solution at the time? The solution doesn't work today, as I will show you in a little bit. But our solution was probabilistic adjacent row activation. Essentially, we changed the memory controller or the DRAM chip. And when the memory controller closes a row, it activates its neighbors with a very low probability. So this is a probabilistic solution. And we show that you get a reasonably good reliability guarantee. If you're not happy with that reliability guarantee, increase the value of P. And with a reasonable reliability guarantee, we show that this is low power, low energy. It's stateless also. So there's a lot of advantages. I like the solution still, but unfortunately today it doesn't work, as we will see, because the RowHammer threshold has gone down to a very low amount. So the number of activates that you need to induce bit flips has gone down to levels of 1,000 or so today, 1,000, 2,000, as I will show you. At the time we tested our chips, it was 139,000. So this problem is becoming much worse. Okay, so this sort of solution can be implemented in the DRAM chip or in the memory controller. I will not go into the details of this. Intel actually implemented a version of the solution in their memory controller. This is not exactly how we envisioned it, but in the BIOS, for example, you can pick your RowHammer solution. You can either pick hardware RowHammer protection or 2x refresh. And if you have hardware RowHammer protection, you have another screen over here where you can choose the RowHammer activation probability. Hopefully you're not going to choose 1/2. Then every activation you're going to get a refresh, which is probably not good. But they actually, this person actually said that 1/2 to the 11, that was our kind of recommendation in the paper. Okay. So this is an example of an intelligent controller. This is a slightly intelligent controller, as you can see, that can do probabilistic activation. I think we need a lot more intelligent controllers to solve this sort of issues. And here I will mention that we've been doing a lot of work on flash memory. This is the FPGA-based infrastructure where we actually built a lot of SSD controllers to understand the issues with flash memory. And we have these intelligent controllers in flash memory. the flash translation layer in flash memory has a lot of intelligence, has a lot of understanding of the device characteristics to fix many different types of errors that are going on in flash memory. And if you're interested, we've written a paper on it some time ago. We need something like that in DRAM, I will argue. Okay, so going forward, I think we need to understand RowHammer. This is a researchy slide. I'm going to get back to what has happened, but there are many effects that still need to be rigorously examined, like aging, environmental conditions, memory access patterns, the system design decisions we make. Without understanding, I don't think we can easily solve this problem. Solving RowHammer is also important. Then the question is, how do we solve it? I think we need flexible and efficient solutions, and also in-field programmable solutions, because you may actually find an effect that you don't know of, as we will discuss. I think co-architecting system and memory is important to avoid performance and denial of service problems. If this is too high level, I'd be happy to talk about in more detail. Any questions?
Yeah.
Yes, please.
So, of course, you could go and hammer and then you can use Bitflips.
Mm-hmm.
But if you just run, normal applications,
Yes.
and you're not trying to do anything adversarial, then, do you see RowHammer problems?
So that's an excellent question. So we did not try to do that. Actually, we're looking at that right now. I think currently it's a lot easier to do that. But one of the industry actually discovered this problem because it happened in a real application. And there's a nice talk from an Intel principal engineer that was delivered at DRAMsec this year. I don't know if it's on YouTube. I didn't put it online. That basically describes how they discovered it. So it happens in real applications. For example, I'll give you the basic idea of how a real application may look like. There's actually an ISCA 2022 paper from Microsoft that shows that there's a coherence-induced hammering. Essentially, if you have a cache block that many processes are trying to access, and that's non-cacheable, that's in memory, you cause a lot of row buffer conflicts in that particular cache block because there's some contention, memory contention. And as a result, you may actually get a bit flip in a real application without someone trying to do this maliciously. Which is scary, I think, because as RowHammer threshold goes down, the probability of that increases in existing systems. Yes?
So setting aside like the other challenges and complications with memories that are not charged with
Yeah.
If you were to just use those, does that automatically solve every problem, or are there still things that come up?
Yeah.
Like the periphery getting interfered with?
Yeah. I mean, so okay, any scaled memory will have some sort of reliability issue, and will have some sort of disturbance issue, and it will get to some level. For example, flash memory. Well, flash memory is charge based. Okay, maybe it doesn't answer your question, but flash memory has actually even worse disturbance issues. But people have shown that in STT-MRAM, for example, you have RowHammer. There are papers that are written on that. They call it RowHammer, but it's some sort of redisturbance issue. So I don't believe that any memory is immune to this problem at this point. These are great questions. Okay, so what happened basically? So Intel actually had this solution, but Intel turned off the solution because DRAM manufacturers in around 2018, 17 through 19 claimed that they actually sold RowHammer. They basically said, okay, our DDR4 chips are RowHammer free. You don't need to have these solutions in your memory controller. And that's essentially what happened. And we questioned that. So we actually did multiple works that tried to understand RowHammer. One of them is more device level. We're trying to understand RowHammer by turning off all of the solutions. I'm going to give you the key idea. Basically, we tested a lot more chips than we did in 2014. We found out that newer DRAM chips are much more vulnerable to RowHammer. We get more bit flips that are happening earlier. And there are new chips whose weakest cells fail after only 4,800 hammers. So this number was 139,000 earlier, as I mentioned. And essentially, existing mitigation mechanisms are not effective. Let me give you, basically, we tested a lot of chips from a lot of different generations, building a lot more infrastructure than I mentioned earlier. Let me give you one example over here. This picture shows hammer count, which is the number of activations or hammers that you need to do to induce the first bit flip. And on the x-axis, y-axis, you have the RowHammer bit flip rate. And these are data generated from DDR4 old, as you can see. When you go to the new chips, this curve shifts to the left and goes up, meaning that you can induce the bit flips earlier and you can induce more bit flips. And that's consistent across all manufacturers, as you can see over here, and many technologies also. Okay, how do the mitigation mechanisms fare? These are simulation results. And again, we see the same on the x-axis. This is the number of hammers required to induce the first RowHammer bit flip. We're marching from left to right, as you can see. This is 100 over here. And this is what we tested as the lowest, about 4,800, I believe. But as you can see, we're marching from left to right. So increasing the refresh rate is a terrible solution. On the y-axis, you see normalized system performance. Your system performance tanks, as you can see. Probabilistic adjacent row activation, if you want to get rid of every single bit flip, at some point it becomes a terrible solution, as you can see over here. So ideal mechanism is not bad. And this is by some definition of ideal. Actually, a really ideal mechanism would be even better, but we're far from ideal over here, as you can see. So there's this paper showed that there's a lot more to do, essentially. We also studied new RowHammer characteristics. There are many dimensions over here. Understanding this problem is actually quite fascinating, I think. We wanted to understand the relationship with temperature and aggressive row active time and spatial locality of the errors, like victim cells, physical location. And we found out some interesting things with our study. We found out that there's no easy relationship between RowHammer vulnerability and temperature. Different cells have different vulnerability. This is very different from retention. This is very different from what I'm going to show you later also. If the aggressor row is active for a longer time, you get actually more bit flips. We're going to delve into that more. And there's a lot of spatial variation in terms of the errors. In certain physical regions of the DRAM, you actually get a lot more errors. So all of these observations actually can be used to build better defenses and better attacks. I'll give you one example. I'm going to talk about this later on a little bit more. Yes, please. Yeah. We're going to get to that. We're going to get to that. I'm keeping the suspense here. Sure. No, none of them was provided to the public. Yeah, basically. But we know what they did because we can reverse engineer DRAM chips. And that's essentially what we did in the next work that I'm going to discuss. Okay, so basically, this is an example. If you actually keep the row active for a longer time, you can reduce the activation count to induce bit flips. And if your RowHammer defense is configured in such a way to not take into account this one, you can actually get bit flips in a chip with a defense. Spatial variation is interesting. We have a paper coming up that takes advantage of the spatial variation. So you can see that 10% of the DRAM chips are a lot more vulnerable than the rest of the 90% of the DRAM chips in general. It's a ballpark. And you can take advantage of that to build a defense improvement. And I'm not going to talk about temperature. If you're interested, you can take a look at it. So we did a lot more analysis. I'm not going to bore you with word line voltage. This is actually fascinating to me because it's a voltage issue. And we actually built a lot more infrastructure to test voltage, change the word line voltage. And you can say that, you can intuitively say that if you reduce the word line voltage, you would reduce the vulnerability because you're not causing a lot more you're causing less disturbance. And that's true. But unfortunately, reducing the word line voltage is not great for data retention time and also activation latency. So you're in a tough trade-off space over here. So there are no easy, let's say, fixes that you can do by playing with voltage, for example. Okay, and HBM chips, talk to me about it. I'd be happy to talk about it. This actually, HBM chips are just as vulnerable as any other chip, essentially. Okay, now let me talk about what the industry did. Industry basically introduced this TRR solution. It's called target row refresh. It's documented in the DDR4 standard, but it doesn't say what is done. Basically, memory controller somehow, or the chip itself does some target row refresh. It's very nebulous. We wanted to understand what this is, essentially. Basically, we essentially refuted this claim that TRR protected DRAM chips are vulnerable to RowHammer. And to be able to do that, we introduced a new type of attack. This is called many-sided RowHammer attack. Remember that actually, without any solution, double-sided RowHammer should be one of the worst type of RowHammer attacks. But if there's a solution inside the DRAM chip that keeps track of how many times you activate the row and refreshes adjacent rows, that was our hypothesis, you can overflow those tables that are inside the DRAM chip that keeps track of the rows by actually hammering many rows instead of just hammering 1 or 2 rows. And we were able to do that basically. We were able to bypass those TRR mitigations by overflowing those tables internally. Essentially, to be able to do that, we need to use our FPGA-based infrastructure to reverse engineer what was happening inside the DRAM chips and also the memory controllers. And we provide an automatic tool that actually created these many-sided RowHammer attacks in DDR4 and LPDDR4 chips that were thought to be not vulnerable. So this is an example of a many-sided attack. Red rows are the aggressor rows. Blue rows are the victim rows, as you can see. So this is assisted double-sided, 3-sided attack, a 4-sided attack. And you can see that even though we don't get bit flips with 1 or 2-sided attacks, we can get bit flips in this particular module after 5-sided attacks. In this particular case, 9-sided attacks, etc. And we were able to induce Bitflips in 30% of the modules from all three major manufacturers. As you can see, in some cases, the most effective attacks were 19-sided. Clearly, there's a trade-off over here. If you increase the number of rows that you're hammering, you have fewer number of activations that you can do in all of those rows within a refresh interval, right? So it's not, you won't get an easy curve over here.
So
Yes.
so
Sure.
what percentage of bits have a memory problem?
A lot, actually. It's actually, like we were able to induce 99% Bitflips in 99% of the bits. Yeah. After you bypass all of these mitigations. This is not the latest work. Yeah, sure.
Roughly, like, what eventually,
Mhm.
you know, like whatever reasonable
Mhm.
refresh
Mhm.
and stuff like that.
Yeah.
And, you know, what percentage of the
I mean, I don't know the exact percentage. It depends on the manufacturer, but I believe, okay, 99% of the rows you can induce. I don't know the exact bits, bit count. Sure.
I think argument is a testing issue, right? Because what
Mhm.
they're doing is they're not testing
Mhm.
for
Yes.
because it's very expensive.
Yes. Mhm.
Then of course there's variability,
Mhm.
like depending on like coupling and stuff like that.
Yes.
That's why I was asking.
It's a very costly test. I agree. Yeah.
Costly.
Extremely
Yeah.
costly.
That's why nobody does it.
Yeah. Yeah. Especially if you include all of those dimensions that we talked about. Yeah. Yeah. I agree with you. Okay, so we showed that this attack works on mobile phones, and different types of attacks can be actually induced in chips that are claimed to be not vulnerable. So this is the summary, basically. I've already mentioned all of these, I think. So these results were actually just scratching the surface. Our tool was not exhaustive. And we basically said that there's a lot more room for uncovering more vulnerable chips and phones. And we did that next, I will describe. But what did the industry do? As a result, basically, our key takeaways was RowHammer is still an open problem. And we argued that security by obscurity is likely not a good solution. I still believe that. And industry is still going through the security by obscurity path. And we're going to talk about the state-of-the-art solutions that are being implemented. Okay, so based on these two works mainly, JEDEC actually finally convened, based on also the push from Microsoft, Google, these hyperscalers. They basically convened the RowHammer group again, let's say, and they basically pushed out these two white papers. If you're interested, you can take a look at them. Some of them are hard to read, but they at least started working on the problem more seriously than before. Okay, what we did later was actually uncovered essentially what was going on in the DRAM chip. I will not go into the details of this. It's actually very interesting. We were able to use the data retention failures as a side channel to detect when a row is refreshed by a DRAM chip internal. If you can actually profile the retention times of DRAM rows, you know exactly when a DRAM row should lose its value. But if it doesn't lose its value, then somebody must be refreshing it internally. And by using the side channel, we figured out exactly how these internal DRAM mitigation mechanisms were working. This is the beauty of retention and refresh. And you can see this like huge table over here, but different manufacturers use different mechanisms. Like they use Samsung, they use counter-based mechanisms. Their capacity is different. It's per bank, and they do a lot of interesting things. But we were able to bypass all of the mitigations on all of the chips that we tested. And we showed that you could actually get up to 7 RowHammer Bitflips in an 8-byte data word. And this was the number that I was quoting. 99.9% of rows in a DRAM bank experience at least 1 RowHammer Bitflip. But I have to get you the number of percentage across the entire DRAM chip.
We could have 7 RowHammer Bitflips, but only a large percentage may not have 7. Right?
That's true. We have that. Actually, I have this over here. This is the distribution over here. Yeah, but a large percentage may still have a reasonable number. So ECC is not at least not a cost-effective solution. Of course, you can make your ECC very strong, but it's very expensive also.
But a checksum technique could have detect.
That's true. Checksum, but that could also be, yeah. Yeah, yes.
Correct.
It won't correct, but it can detect.
Detection techniques should work.
I agree. But we want to, I think maybe we'll get, yeah, sure. We want to get rid of all of these Bitflips, right? We don't want to have any corruption. Okay, so industry was also working on it, which is interesting. Microsoft did a lot of work on this topic, but Google introduced a very interesting attack. They called this the half double. There are a lot of interesting internal mechanisms, but they basically showed that if you can have a far aggressor, this is a far aggressor, this bold red one. And if you hammer that many times, and if you hammer a near aggressor very little times, you get errors in this victim. Now, this may not sound that interesting, but it's actually very interesting because this makes the defense mechanism an attack itself. Why? Because if you're hammering the far aggressor, the defense mechanism would be refreshing the near aggressor, and the defense mechanism itself would be working as an attack. So that's the problem, basically. That's why this is so fascinating, I think. Okay, so your defense mechanism needs to take into account this one also going into the future. So I'm going to talk about defense mechanism a little bit more about intelligent memory controller. I'm going to give you another idea that doesn't scale very well, even though we came up with it. Our goal was to actually scale with worsening RowHammer vulnerability and be compatible with existing commodity DRAM chips without changing any of the interface or the chips. And the idea over here, I think it has merit still, but it needs to work. It needs to be made more scalable. Essentially, we use area-efficient Bloom filters in the memory controller to detect potential aggressor rows, and we selectively throttle accesses to those rows, and such that bitflips do not occur. You can prove the security properties of this, and one of the benefits of this sort of detection is you can optionally inform the system software about the attack also. So this works if your RowHammer threshold goes down to 1,000, meaning 1,000 activations can go as a bitflip. But if it goes below, which is the regime we're going towards today, the solution actually has higher overheads. So this is another example of an intelligent memory controller, I believe, that we need to be building. Okay, so we go back to these solutions. What did the industry do finally? So this is from February 2023. Finally, a major DRAM manufacturer acknowledged the problem by writing a paper about it at ISSCC. And they talk about their solutions as SK Hynix. And they essentially implemented a lot of the variants of the ideas that were disclosed in prior research. What they did was they actually modified the DRAM chip. This was something that nobody thought people would do, but they actually added counting cells. Essentially, for every row, they added a cell to count how many activations there was. And there's a small memory controller inside there that refreshes adjacent rows. They don't talk about the details of their mechanism, but they say that they reduced the RowHammer vulnerability to 7%. Whatever that means. We don't know if that's true. That remains to be, of course, examined. But this is a step in the right direction, in my opinion. But I believe the current DRAM interfaces do not allow this to be nice, let's say. We're going to talk about that. Of course, Samsung, after they saw SK Hynix's paper at ISSCC, they had to put a paper on archive that talks about their mechanisms. Their mechanisms are also an approximate counting-based mechanism, which is also interesting. This is very hard to read, but you can take a look at it. So, okay, the question is, of course, are we now RowHammer free? I'm not going to answer that question, but I'm going to answer something that says maybe we have other things to worry about also in addition to RowHammer. Any questions so far? Okay, so I'm going to talk about RowPress. This is something that we demonstrated at this ISCA. This is another disturbance phenomenon that caused bitflips in real DRAM chips. And it's actually different from the RowHammer vulnerability, but it amplifies RowHammer vulnerability. And we demonstrate on real DRAM chips, and also using a user-level program, we demonstrate the proof of concept, let's say. We provide some solutions also. So what's the problem? Basically, I mentioned to you earlier that keeping a DRAM row open for a long time caused bitflips in adjacent rows. But in this particular case, we kept the DRAM row open for much longer. And we saw actually very few activations are needed to cause bitflips. In some extreme cases, where you violate the timing parameters, only one activation is enough. This is fascinating to me because you essentially activate one row and you wait for 30 milliseconds, charge gets depleted in another row, adjacent row. Clearly, this is violating parameters, but it's still interesting from a device perspective. So basically, why did we want to look at this? Essentially, if you have a solution that looks like this, if that doesn't rely on a high activation count, you can bypass it with this sort of mechanism. This is my student's drawing. I like that one. But basically, instead of relying on a high activation count like RowHammer attacks used to do, this is the minimum row open time that you can have in DRAM. Just keep the row open for a longer time, which increases the disturbance that happens to the adjacent row. Then you need very few activations, essentially. That's the idea. And these are real numbers from one particular chip. And we, of course, amplified our infrastructure to test this. And at this point, we're actually releasing the names of the manufacturers. At some point, we were not, but I think people can replicate our results much better. So essentially, there are two key conclusions that we have. RowPress significantly amplifies vulnerability to read disturbance and has a different underlying mechanism than RowHammer. So these are results from real chips. This is the RowHammer domain, let's say. You keep the row open only for 36 nanoseconds. This is where you keep the row open for 7.8 microseconds, which is allowed by the standard. You keep the row open by 70.2 microseconds, which is also allowed by the standard if you actually push the refreshes or pull the refreshes early. You can see that there's a clear reduction in the number of activations that you need to do to induce the first bit flip. And at 30 milliseconds, all of the chips yeah, essentially all of the chips from all manufacturers get Bitflips. So this is the number, basically. You reduce your activation count by 1 to 2 orders of magnitude. Interestingly, this phenomenon gets much worse as temperature increases. This also indicates that this is different from RowHammer, the underlying disturbance mechanism. And a different set of cells actually gets corrupt compared to RowHammer. And there are differences in terms of access patterns and temperature changes, as our paper discussed. I'm not going to go into all of these details since we don't have time. So we also developed a proof of concept using an Intel Comet Lake processor and a real module that has RowHammer protection. And basically, our hypothesis was we could keep the row open by accessing the cache blocks in the same row using a program. And the memory controller would hopefully keep the row open. Existing memory controllers, most of them have adaptive row open policies. If you keep accessing the cache blocks in the same row, they keep the row open because they want to improve row buffer locality. And that's what we did essentially. Of course, you need to, this program is a little bit more complicated than this because you need to synchronize with the refreshes, etc. But we varied this parameter number of reads that essentially changes the number of cache blocks that you access in a row. And with the RowHammer, classic RowHammer, we don't see Bitflips. But as you increase the number of cache block reads, you start seeing Bitflips. And there's clearly a trade-off. After some point, if you actually read too many cache blocks, you cannot hammer the rows enough times. That's why those Bitflips go to 0 after some point. Okay, so how do you fix this problem? So clearly, you can fix it by adapting the RowHammer mitigations, and that was our proposal. There are other fixes that you can discuss, like changing the DRAM, etc., that we also discuss in the paper, but I'm not going to discuss here. But if you already have a RowHammer mitigation in place, the key idea here is to limit the maximum row open time first. Don't make it infinite or 70.2 microseconds. Make it something small so that you can exploit some row buffer locality, at least for performance. But configure the RowHammer mitigation. Basically, RowHammer mitigation kicks in based on some RowHammer threshold so that you can actually account for the reduction in activation counts that leads to a bit flip, such that RowHammer mitigation kicks in earlier if you keep the row open longer. That's the idea over here. And that's picture kind of summarized. Of course, with this one, you get a little bit low row buffer locality exploitation, but hopefully you're secure. Well, you can prove that you're secure actually if you set your parameters right. But setting those parameters right actually is a difficult part, as we will discuss a little bit more. So we show that you can actually do this with low performance overhead. But in extreme case, you can actually get high performance overheads also. Okay, there's a lot more in the paper that I will not talk about, but I'm happy to discuss more. Any questions on this? Yes, please.
I might have missed, how do you keep the row open for longer from like software perspective, or is that something you did it in a control setting?
Like there are some parts of DRAM which could get access very often, like let's say
Yeah.
but there are other parts of DRAM which you're just going to take and throw into the cache, for example. Can that be a system level solution to this problem?
So yeah, people have developed system level solutions like protecting the page tables, for example, or adding more isolation. There's a paper in SOSP that's happening right now, actually, that shows that you can partition the applications across different subarrays such that they don't interact with each other. Certainly, those are viable. They don't solve the, let's say, all of the robustness issues. They may solve the security issues that happen across applications, for example, but they may not solve the safety issues, for example, right? Yeah. Yes, please. So RowPress. Okay, so there's we can go into more detail, but there's a passing gate effect that happens. Essentially, it's electrons get injected through a passing gate. Hopefully, that gives you at least a keyword. Yes.
Question. Every time you flip a bit, there's a current spike.
Yes.
And that would have some magnetic effects.
Hmm.
Some conductive.
Yeah.
There must be some conductive effects.
Yes. So you're suggesting you can detect this, and maybe that could be a solution, or? Okay, so maybe we can talk about the device level issues later on. I wanted to keep the abstraction level lower, higher, but there are a lot of interesting things, and people are also examining this. People are trying to model this using TCAD simulations, etc. It's not easy, essentially. But those two things that I mentioned earlier, like crosstalk and electromigration, is the electromigration and injection are the two major mechanisms that we know of that leads to RowHammer. RowPress is the passing gate effect, essentially. Yes, please. Yeah. I mean, depends on your perspective, right? I believe it's a huge problem. I don't think we should have any Bitflips in our systems, but this is also a very cost-sensitive part. So anything that you do is increasing your cost in the end. From the DRAM manufacturer's perspective, it's not like they're completely dragging their feet. They're trying to solve the problem, but I believe they don't know exactly how. And I think all of these issues that we have discussed affect them directly. For example, aging of DRAM chips, right? I'm actually very worried in an aged DRAM chip, this could actually become much worse. That's something we're working on. So I don't think there's so many dimensions to the problem that it's not easy to solve, in my opinion. But they did drag their feet initially, I would say. Right now, I don't think they're dragging their feet. But they just don't know easily how. Okay. Okay, I believe there's more to come, by the way. So hopefully we'll discuss that. So I think these are the two major directions that I would like to bring up. I think we need to understand these Bitflips a lot more, and also hardware errors in general. I generalize things a little bit. Aging, environmental conditions, memory access patterns, system design decisions that we make, all of these are actually, I think, quite difficult, and we need to understand them. We don't understand some of these. And solving is also important, I think. Flexible and efficient solutions are necessary, and I believe some of these solutions need to be patchable, reconfigurable, programmable. And I believe we need to co-architect across the system and stack and components. We have some minutes, I think. Feel free to think about questions, but I'm going to mention something. I think one of the things that limit innovation in this area and that makes solutions harder, this also goes back to your point, I think, is the interface between DRAM and the memory controller. This is a very rigid interface. Memory controller right now does all kinds of maintenance that I believe DRAM should be doing. That's one of the reasons I think the DRAM manufacturers are not able to do a lot of things, because they have very little time budget to do some sort of RowHammer mitigation, for example. So this is a paper that keeps getting rejected, but I believe it's a good idea. So the idea is basically very simple. Give some autonomy to the DRAM chip such that the DRAM chip can do some things internally. We call this self-managing DRAM. And the DRAM chip at some point can say, I'm not going to service your activate because I have some much more important things to do. And that's the idea. This is very little change to the interface. We have an NAC pin essentially. Leveraging the ability to reject and activate, a maintenance operation like RowHammer mitigation can be implemented completely within a DRAM chip. And I believe this is a good partitioning of the duties, let's say. And it's not just RowHammer protection. You can actually do a DRAM refresh mitigation. A lot of the things that we have discussed, the DRAM manufacturer can figure that out, and it can do variable rate refresh, etc., without modifying the memory controller. I mean, they have a memory controller internally, of course, now, memory scrubbing, etc. I'm not going to the details of this, but I believe this sort of interface changes are going to be important going into the future, except it's a tough area.
I think those people don't want to spend any money on logic gates, right? That's the question.
Well, I think that mentality is changing. It's a mindset issue, but I absolutely agree. That mentality was changing because, like, they've clearly introduced these RowHammer counting cells, so they're adding logic gates. They're actually experimenting with processing in memory mechanisms. So I believe that mentality will change. I believe they need to change the business model slightly. We need to get out of this memory being commodity. And once they change that business model, then I think they can justify a lot more of those logic gates. And maybe we'll have a much better, let's say, system going into the future. Yes, please.
Your proposed solution, right? And in that case, is there a possibility of denial of service attacks? Because if someone exploits the DRAMs, whatever mechanism.
You mean for this? So absolutely. But that's true for any RowHammer solution. Meaning, if you actually have a RowHammer solution that's perfectly secure, you can actually cause denial of service by actually attacking a row, because internally there will be a lot of refreshes that's going on. But that's true for this interface also, and that needs to be examined. So denial of service, I think you need to be careful about. But at least you're not doing data corruption. Denial of service, hopefully, a little bit easier to deal with. In the end, I think it'll be degradation of service and not complete denial also. Yeah. Okay. Okay, so since we don't have a lot of time, I will go through this relatively quickly. I think future is more bleak, basically. Due to difficulties in technology scaling, we're going to see more of these errors. And some of them may be happening and we don't see them. They may be going unnoticed. And I believe we need to examine these. These errors can cause safety, security vulnerabilities clearly. And this is true for all technologies. There was a question earlier on different technologies. I don't believe any technology is immune. We have not come up with a magic memory technology yet, even though some people in the past have claimed that some technologies over here on this list were magic, let's say. So how do we deal with it? I think we need to understand more. I'm not saying anything different. We need to have more real device data and analysis, modeling, better understanding, developing reliable metrics, models. We need to architect better. We need to have better partitioning of duties across the stack. I think one of the reasons we are suffering today is because of that bad partitioning of duties across the stack that we have between memory and processor. We clearly cannot give up performance and efficiency, but patchability in the field is important. And I think design and test, as Subhashish mentioned earlier, is going to be a lot more important going into the future. Maybe it's going to be a lot more online testing to actually figure this out, because offline testing is, I think, in my opinion, it's insurmountable in terms of cost. Yeah. Yeah, it's all online, I think. Okay, that's why we've been building this infrastructure, and I think we need to build more. So let's get back to bridges. Bridges have Bitflips, as you can see, and human beings have been building bridges for thousands of years, and this is critical infrastructure. And we still haven't gotten it right. This is Seoul, this is Minneapolis, Genoa, and more recently Pittsburgh, where I used to live in. I used to go over that bridge many times. Yeah, this is the Forbes Avenue Bridge, if you know Pittsburgh. Yeah. I think we're better than bridges. I mean, here we're at a scale that's much larger than bridges. We have billions of devices, clearly, but at least we have some better hope. And bridges are very hard to, let's say, patch, if you will, right? But intelligent memory can actually patch those failures. Okay, let me give you some final thoughts. I like this paper. This was published in IEEE Security and Privacy in 2003. Actually, took advantage of Bitflips in memory to take over a virtual machine. It's essentially a very similar attack to what Google developed using RowHammer. And the way they actually induced memory errors was actually put a lamp on the system over here. So you get a lot of memory errors, clearly. It's a probabilistic attack, etc. So what RowHammer did was essentially replace that lamp with software. You have a simple exploitable memory error that can be induced by software. And that's why people are writing articles that look like this now. And there's more coming. Okay, I'm going to skip some of these over here to get to the end, to conclude, since we don't have time. So to conclude, memory reliability is reducing. These reliability issues open up security and safety vulnerabilities. These are very hard to defend against. Some people say that these are Byzantine failures. Do all you can to avoid them. And that's, I believe, true. RowHammer is a prime example of this. As far as we know, it's the first example of how a simple hardware failure mechanism can cause a widespread system security vulnerability. And I find the implications on system security and safety research tremendous and exciting. The bad news is this is getting worse, and there are other effects that are coming up that we need to understand. The good news is we have a lot more to do. At least, hopefully, we're now fully aware that hardware is easily fallible. There's a lot of issues in hardware, and I think we need to really be solving all of those. We're developing both attacks and defenses, at least from a security perspective. And we're hopefully developing more principled models, methodologies, and solutions. I think we need to do a lot more on this last one over here, because I think understanding is lacking in this area that leads to holes that are open. So I'll acknowledge my group over here. You can take a look at some of these faces. And everything I've discussed is online. You can take some of the source code, run it on your laptop, see if it caused Bitflips. And it's on our GitHub. I'm happy to take more questions.
Thank you. Questions?
Yes.
So you mentioned that IEDM is potentially
So yeah, that's a good question. So we've tested HBM2 chips, which is not the latest and greatest HBM3 clearly, but that's what we had access to. I think there are effects in HBM that is one of the issues, like temperature is one of the issues. I mean, you see a clear problem with RowPress, especially in HBM, because of the 3D stacking and temperature. And also, we're investigating some 3D stacking related issues that may not exactly be like RowHammer, but there are some other Bitflips that you can get in HBM, I believe. We have a paper that's on archive if you're interested in taking a look at HBM2 results. Yes.
So I guess this is more of a question. Generally, memory is all interconnected arrays, right? Very dense crossbars. Is there? It seems like there's no hope, right? Like every dense architecture probably itself will have some level of these.
Yeah.
Is that your thought as well, or?
I mean, I don't think it's a fundamental issue with the interconnectedness, right? It's I would say it's more of a hierarchical structure, right? But density, certainly, yes. I would say, yeah, because of the density and closeness of these structures to each other, you will have some noise between those structures. And that's what we're seeing with RowHammer and certainly RowPress. And that's why we're not seeing it in older technologies that are not as dense. Does that answer your question? I don't think it's fundamentally an issue of things being interconnected, right? It's just how closely they are, how close they are to each other.
I think the bigger issue is that, as I said, that in memory-only chips, especially, nobody wants to spend logic gates to do anything, And, if you have, just memory and nothing else to get around anything, like, what are you going to do, like, which is kind of, like, whatever Hynix did, they had to put in some gates to
Yeah, yeah. Samsung also, actually.
Yeah, they have to put some intelligence in the memory chips, otherwise, and the farther away you go from memory chips and you try to solve the problem somewhere else, your visibility and diagnostic into the whole thing is just not going to be there. And then you just, just guess and do guesswork, kind of a similar thing is happening in logic chips now, right? Like there's a paper at SOSP from Alibaba, like following up on the Google paper. The logic chips, like a significant percentage of logic chips are defective in the cloud. People expect 100 defective chips per million. The number is at least an order of magnitude more, if not much more than that.
And it's going to get worse. It's not going to get better.
Like when something fails, people are just, like throwing darts in the dark and they're hoping that something good will happen. And they cannot diagnose what the source of the problem is.
Yeah, you mentioned attacks on AI, let's say inference getting worse or worse. Have you seen the real examples, or is this more something you've seen in the lab? Possibility, or how should we think about? I mean, since AI safety is such a big deal these days, is this a big risk or just a hypothetical?
Well, I don't know if there are real examples out in the field, but people have shown that using these Bitflips, you can actually destroy the accuracy of real inference engines. There are a lot of works on this topic. I believe it's a clear critical safety issue, yes. I mean, also, like related to RowHammer, we don't know if there's an attack that's out there that affects everyone, but if you don't expose these things, probably those attacks may be happening also, right? I think that's always the thing in the security research. Yes.
I feel like, especially in the DRAM market, which is commodity market, like everything is spec driven, right? How much can you put into this particular DRAM? Have you ever thought about, or has the industry thought about solutions where they have some sort of benchmarking or some sort of testing environment, which would like at least help, standardize this across chips? Like right now, I don't see this as part of my DRAM spec list when I'm trying to buy something. Right?
I mean, this is something that DRAM manufacturers don't want to expose, basically, because exactly, they don't want you to know the reliable characteristics. So this is something that we've been arguing also: more transparency in the reliability characteristics, a better interface, better partitioning of duties. All of these actually go toward that direction. Actually, in one paper we have on archive, we argue something like that. DRAM manufacturers expose some characteristics such that the memory controllers can be built on top of them to achieve system level reliability and robustness guarantees. So I agree with you, but it's not easy to move in that direction.
But there is another issue, right? So to be able to even figure out what those characteristics are, that means they have to characterize them, and it's highly unlikely that they characterize it one time and it will hold for the whole batch, right? So you pretty much have to do it chip by chip, which means now it's more testing cost and this and that. Right?
Exactly. Yeah, I mean, there's certainly to answer some other part of your question, there's certainly testing programs that you can download and use, right? MemTest 86, for example. In fact, those were the first folks that picked up on our original paper and added a RowHammer test, and then everybody was going to them and saying, "Oh, we have these Bitflips in this RowHammer test." So basically, certainly you can do testing after you assemble your system. And people try to do testing, but testing is a very tough thing, right? As Subhash also mentioned.
Thank you.
Yes. Who wants to go first?
These three, like you.
So on the sensitivity that you saw from different combinations, sometimes you said that if you just access the whole line for a long time, but you will not have it effect. So do you think that influence mainly with the access transistor or with the dimensionality of the capacitance, or just with the density of the interconnector?
I think
Well,
it's all of the above.
It's all of the above, probably, yes. I mean, we can go into the silicon level mechanism if you want, but it's all of the above in the end. It involves all of them. Yes.
So, area.
Cost.
Yeah, and cost, right? So one of the things is that sometimes like Caroline talks about is having security be a first principle. So how do you think we can teach like students and researchers and people in the workforce who are designing these devices, designing these architectures, designing these systems, to think about that from like a systematic approach, like this is the trade-off space, and then instead of just doing the best performance, but blindly ignoring security until someone comes up with an impact, like considering that trade-off space, and then maybe knowing, okay, I know that I'm not secure, but at least I know it, and I know where I stand on the trade-off curve. Do you have any ideas on like this, that method?
Well, yeah, I mean, that's why I propose this understanding. I don't think we're even at the point of where we have understood that curve, for example. But I mean, it's a tough thing, right? It's not just performance, I think. So in the end, if you want to get lower costs, if you want to get larger memories, and that's what we want, that's what everybody wants, you will have to scale the memory technology to some smaller dimensions, and you will run into these reliability problems. I think it's more of a mindset issue that these reliability problems are also important, and people need to be educated on that. And there's a solution space. There's a variety of solutions that you can employ.
But I think you're like, instead of kind of designing first that at least falls higher up.
Yeah, so that's an excellent question. If you want to design something that is like highly reliable, etc., the cost is always going to be higher. You could do it. Like people are trying to do that for space applications, for example, right? Things that are going to go out to space, hardening, many modular redundancy, etc. We know the design principles over here, and we send these things into the space also, but cost is very high. Yes,
But I think there's another issue, which is, given what we have done I actually jokingly say it's the 19th century approaches, but I mean the 20th century approaches. It had been a very manufacturing driven industry. And, and that's why I think we don't even know what we don't know. I mean, like to be able to solve these problems, you have to know. And I think that's a huge issue.
Yeah, that's why my first point was understanding. I think I agree with that. We need to know more about what we manufacture, I think.
You have a question?
With respect to the security, is there anything that operating system in terms of like how position addresses are creating an accuracy or things like that?
Yeah, I mean, there are papers on that topic. One of the ideas is physical isolation, meaning waste some of your memory such that the rows that you are accessing, there's no data that are next to those rows. But this wastes a lot of memory, clearly. And people have tried to overcome the memory overhead. So you can isolate different applications to different subarrays where you don't have RowHammer across subarrays. So there are some things that you can do.
But you need to know the layouts of the DRAM.
That's right. A lot of these can be reverse engineered.
Yeah.
Yes, that's what they, sure. Yeah, that's the downside. You need to know the layout of DRAM. So you may not be perfectly correct. But yes, people have proposed a lot of those solutions.
This is the last question. And then we're done.
This type of solution as a solution. So you have two adjacent rows and place those two capacitors in a different layer, so we have more distance between the neighboring capacitors. I know that it's very deep, but this type of solution has been discussing in logic device to avoid cross-couple or coupling capacitance in very low metal layers.
So what would, but then you will waste space.
But then,
one of the layers,
either
right?
you waste space or you could have something else come next to it, and then that will become the.
In a different case, we can still have the same number of capacitors.
But you will waste space in one of the layers, right? In each individual layer.
Yes.
Yeah. So I think that's absolutely. I think the solutions can waste space. So, for example, DRAM manufacturers can insert additional distance, etc. It's not easy in today's technology, but you can reduce the distance, increase the distance, etc. And you can reduce this problem. No question about that. But all of those solutions come at cost, price, basically.
Okay. Thank you very much, Onur.
Sure. Thanks. Yeah. Thank you for the questions.